This is lecture 19. I'm going to go over some of the problems from homework 10. In the last lecture, I did exercises 1 and 2. So today I'm going to do 3, 4, 5, and 6, and the 2 more exercises that I'll do in the next lecture. So what is exercise 2.2.3, which is to determine the subgroup lattice of the group of symmetries of a rectangle. So here is a rectangle. It's not a square. So let me label the vertices 1, 2, 3, 4. And what are the symmetries of the rectangle? What are all the ways we can pick up the rectangle, not tear it or cut it, but just twist it, turn it, rotate it, so we put it back in the same space? So of course, one symmetry is the identity. It's called E. So the identity symmetry just leaves the rectangle exactly where it is. Another symmetry would come by rotating the rectangle around a vertical axis. So 1, 4 move from the left to the right, and 2, 3 move from the right to the left. So we can pick up the rectangle, turn it, and put it down like this. Call this X. That's symmetry. We also have a symmetry where we take our rectangle and rotate it around a horizontal axis. So 1, 2 on the bottom moves to 1, 2 on the top. The top 4, 3 moves to 4, 3 on the bottom. And there's one other symmetry. So let's just call this, so this is this horizontal symmetry. I call this Y. And there's one other symmetry where we can take the rectangle, rotate it vertically to get this, and then rotate it horizontally. So when we do that, the 2, 1 on the bottom is on the top, and the 3, 4 on the top is on the bottom. Let's call that symmetry Z. And if you look at this, you'll notice in these 4 different symmetries, the vertex labeled 1 ends up in all the 4 possible corners. And once you put down the rectangle in the space with the 1 in a certain corner, the short side has to be 1, 4. There's no other option for that. So these are the only possible symmetries of the rectangle. So this symmetry group, let's call it G, consists of E, X, Y, and Z. And we saw, how do we get Z? We did a vertical and then a horizontal rotation. So Z is in fact equal to Y times X. And in fact, if you do first a horizontal rotation and then a vertical rotation, you'll get exactly the same thing. So XY is also equal to Z. And these symmetries have the property, well, E is the identity. But if you, for example, rotate vertically twice, you get back the identity. So E equals X squared. If you rotate vertically twice, you get back the identity. So E equals Y squared. If you do this horizontal and vertical followed by another horizontal and vertical, you'll also get back to the identity. So X, Y, and Z each have order 2. So what is the lattice of subgroups? So the biggest subgroup is always the whole group. And the smallest is the subgroup that consists just of the identity. But we have three subgroups of order 2. We have the subgroup generated by X, the subgroup generated by Y, and the subgroup generated by Z. So this diagram is the lattice of subgroups of the group of symmetries of the rectangle. Right? That's what it is. Let me skip number 4 for a moment and go to 2.5 and 2.6. Let's start with a clean piece of paper. What is exercise 2.2.5? We let R theta be the matrix cosine theta, sine theta, minus sine theta, cosine theta. And we look at the set of all R theta for all possible numbers theta, theta in R. And this is called the rotation group. And we call this rotation by an angle of theta radians. And why is this a rotation? So if you think of this as a matrix acting on vectors in the plane, so here's the plane, and we have the unit vector E1 and the unit vector E2. E1 is 1, 0, E2 is 0, 1. So what does R theta apply to E1? That's cosine theta minus sine theta, cosine theta, applied to the vector 1, 0. So you know matrix multiplication. This is cosine theta, sine theta. Where is that vector? Well, if this is the angle theta, if we rotate this unit vector by theta, we get exactly cosine theta, sine theta. So this matrix rotates E1 by theta 1 radians. What about E2? What does R theta apply to E2? We have cosine theta, sine theta, minus sine theta, cosine theta applied to 0, 1. This is the vector minus sine theta plus cosine theta. If theta is between 0 and pi over 2, this is negative and this is positive, so we're in the second quadrant. And in fact, we have exactly this vector. This is an angle theta. This is the vector minus sine theta, cosine theta. So this is not part of the problem, but this is just so you understand the meaning of this matrix as a rotation. Applied to any vector in the plane, R theta rotates it counterclockwise, that is in the positive direction, around the origin by theta radians. And we want to show that this set of rotations is a group. So we have to show that it's closed under multiplication, for example. So if I take R, let's say R theta, times, and I'll take another angle. I'll call it, let me call this R alpha and R beta. So this is cosine alpha, sine alpha, minus sine alpha, cosine alpha. That's R alpha. And we're multiplying it by the matrix R beta, which is cosine beta, sine beta, minus sine beta cosine beta. So you know matrix multiplication. This is cosine alpha cosine beta minus sine alpha sine beta. And first row, second column, we get minus cosine alpha sine beta minus sine alpha cosine beta. And second row, first column, sine alpha cosine beta plus cosine alpha sine beta. And minus sine alpha sine beta plus cosine alpha cosine beta. And then you are expected to know trigonometry. And the addition formula for the cosine and the sine say this is the cosine of alpha plus beta. And this is minus the sine of alpha plus beta. And this is plus the sine of alpha plus beta. And this is cosine of alpha plus beta. So this is exactly the rotation matrix R alpha plus beta. So the product of two rotations is a third rotation. So this set is closed under matrix multiplication. What is the identity? What is R0, rotation by zero? That's cosine 0 minus cosine 0 sine 0 minus sine 0 cosine 0. Cosine of 0 is 1, sine of 0 is 0. This is the identity. So R0, that's the identity. The identity matrix is in this set. And if I take beta equal to minus alpha, R alpha, R minus alpha, by this addition rule, is R alpha minus alpha, which is R0, which is the identity. So the inverse of the rotation R alpha is rotation by minus alpha radians. So this proves that the set of rotations is closed under matrix multiplication. It contains the identity matrix, and it contains the inverse of each matrix. So it's a group. So that's exactly what we needed to prove. This is part A. Part B is to let J be the matrix 1, 0, 0, minus 1, which they call reflection, reflection in the x-axis. And why is that? If I apply the matrix J to the vector xy, 1, 0, 0, minus 1 applied to xy is x minus y. In other words, if here we have xy, this is x minus y, which is j of xy. So we're reflecting through the x-axis. So this is the matrix of reflection through the x-axis. What is j times the rotation? That's 1, 0, 0, minus 1, cosine theta, sine theta, minus sine theta, cosine theta. If we do our matrix multiplication, that's cosine theta minus sine theta minus sine theta minus cosine theta. Mhm. What is r theta, r minus theta times j? So r minus theta times j, r of minus theta is cosine of minus theta, sine of minus theta, minus the sine of minus theta, cosine of minus theta, times the j matrix, 1, 0, 0, minus 1. But you remember that the cosine is an even function. Cosine of minus theta is the same as cosine of theta, and the sine is an odd function. The sine of minus theta is minus the sine of theta. So let's see, if I multiply this out, what do I get? I get cosine of minus theta minus the sine of minus theta. Oops, is that right? Sine of minus theta. First row, second column is minus sine of minus theta times minus 1 is plus, and minus the cosine of minus theta. But if we use these identities, cosine of minus theta is cosine theta. Sine of minus theta is minus the sine of theta, minus the sine of theta, minus cosine of minus theta is minus cosine theta. And you see, this equals this. This equals j times r theta. So that's the identity that we were asked to prove in part B. Let's see. What is part C? So in part C, we let j theta be the reflection through the line containing the origin and the point cosine theta, sine theta. So you remember from pre-calculus, for example, if you take the unit vector and rotate it by an angle theta, this point has coordinates cosine theta, sine theta. And we're looking at the line going through the origin in this point. And we want to consider reflection through this line. That is, if we take a point, xy, you draw the perpendicular to the line, and then you go the same distance in the opposite on the other side of the line over to here. So this map that sends this vector to this vector, you're reflecting this vector through this line that makes an angle theta with the positive x-axis. So if we were to call this vector v, this would be j theta of v. And we want to compute j theta. So let's figure out how to do that. Let me draw the picture again. Here's a line that makes an angle theta with the x-axis. And we take a vector v and we reflect it through this line. This is j theta of v. And we want to find the matrix that sends this vector to this vector. So how can we figure out what is the matrix for the reflection of the vector through this line? So the matrix, we call it J theta. The first column is what happens to the unit vector E1 when you reflect it through this line. So to reflect E1 through the line, you draw this perpendicular and go this distance. That's exactly the same as rotating this vector through 2 theta radians. And if you take the unit vector and rotate it by 2 theta, the coordinates are cosine of 2 theta, sine of 2 theta. Right? That's easy. Suppose we take the unit vector E2 and we reflect it through this line. So that means you take the perpendicular to the line, and then you get the same distance on the other side of the line, and you end up over here. We have to find the coordinates of this point. So this is the same as taking this point and rotating it through this angle. What is this angle? Well, if this is theta, and this is pi over 2, this angle is pi over 2 minus theta. And then so this is a rotation through pi over 2 minus theta. And then we rotate a second pi over 2 minus theta. So we get to the angle theta minus pi over 2 minus theta, which is 2 theta minus pi over 2. And what are the coordinates of this point? Coordinates of this point will be the cosine of 2 theta minus pi over 2 and the sine of 2 theta minus pi over 2. And if we write this in terms of, we'll just for example, use the addition formula, the cosine of 2 theta minus pi over 2 is cosine of 2 theta, cosine of minus pi over 2, which is 0, minus the sine of 2 theta, sine of pi over 2, which is 1. So we get, this is a 2, sine minus, you get the sine of 2 theta with a minus sign. Let's see, let me just double check. Cosine 2 theta, cosine pi over 2, minus sine of 2 theta, sine of minus pi over 2, which is plus the sine of pi over 2, so that's a plus sign. And expanding this by the formula, the subtraction formula, if you like, sine 2 theta cosine pi over 2 is 0, plus cosine of 2 theta times the sine of minus pi over 2, which is minus 1. So the matrix for reflection through the angle theta is through the line that makes an angle theta with the positive x-axis is over here we have sine of 2 theta minus the cosine of 2 theta. So that is the matrix that we calculate. This is a hard calculation. You really need to be familiar with this elementary vector analysis in the plane. And we want to show that we can write this in terms of r theta and j in 2 different ways. So if we take, for example, r theta j, r minus theta, that's the matrix cosine theta, sine theta, minus sine theta, cosine theta. times the matrix 1, 0, 0, minus 1 times r minus theta. Cosine of minus theta is cosine theta. Sine of minus theta is minus sine theta. Minus sine of minus theta is plus sine theta. And cosine of minus theta is cosine theta. So what I have is cosine theta minus sine theta, sine theta, cosine theta. This times this is cosine theta, sine theta, sine theta minus cosine theta. And when I multiply these two matrices together, I get cosine squared theta minus sine squared theta, sine theta cosine theta, plus another sine theta cosine theta makes that 2. Here I have sine squared theta plus cosine squared theta. So sine squared theta minus cosine squared theta. And, sorry, let me do this right. First row, second column is sine theta cosine theta plus another sine theta cosine theta, makes that 2. And second row, second column, I have sine squared theta and minus cosine squared theta. And this I know is the cosine of 2 theta. This is the sine of 2 theta. This is the sine of 2 theta. And this is minus the cosine of 2 theta. So if you look at this matrix and this matrix, they're equal. So I have this representation of this as this product. And the final part is to show, the final part of this part is to show that j theta is equal to r2 theta times j. So reflection through the line theta is obtained by reflecting the vector through the x-axis and then rotating it by 2 theta. So let's calculate this. R2 theta is cosine 2 theta sine 2 theta minus sine 2 theta cosine 2 theta times 1, 0, 0, minus 1. This is cosine 2 theta sine 2 theta sine 2 theta minus cosine of 2 theta. This checks. This is equal to reflection through theta. Let's look at part D. Suppose we let r be rotation in the plane by an angle of pi over 2 radians. Let's consider the set of r to the k, j to the l, where k runs from 0 to 3, and l, these are integers, 0 or 1. So we have 4 choices for k and 2 choices for l. So this contains at most 8 matrices. And let me call this G. I want to show this as a group. So R is, well, R to the 0 is the identity. R to the first power is rotation by pi over 2. r squared, that means r times r. I'm sorry, that means r pi over 2, r pi over 2. That's r pi over 2 plus pi over 2. That was our addition formula for rotations, or r pi. So this is rotation by pi radians. In r cubed, you rotate pi over 2, pi over 2, pi over 2. That's rotation by 3 pi over 2 radians. So you have rotation by 0, the identity, rotate by pi over 2, rotate by 2 pi, rotate by 3 pi over 2. So these are what these 4 rotations consist of. And what about Rj? Well, that's interesting because we proved in the previous section, so let me just say, by part C, reflection through the line theta is equal to R2 theta times J. So we have J, which is the rotation through 0 times J. Let me do it like this. What is R pi over 2 times J? Well, by this rule, pi over 2, so this is R, 2 times pi over 4 times J. So this is reflection through the line pi over 4. R pi J is R 2 times pi over 2 times J. That's reflection. Well, that's reflection through the y-axis, pi over 2. And R 3 pi over 2J. So 3 pi over 2 is 2 times 3 pi over 4 times J. That's J 3 pi over 4. So reflection through the x-axis is J. J0. Reflection through the line pi over 4 is J pi over 4. Reflection through the vertical line, J pi. Reflection through the y equal minus x line is J 3 pi over 4. So powers of R give you powers of R. Anything of the form, one of these rotations times J is one of these 4 reflections. Reflection through x-axis, y equals x, y-axis, y equal minus x. Now, we want to show this forms a group, and it's isomorphic to the group of symmetries of the square. So how do we show that it forms a group? Well, there's always an easy way and a hard way, but there's one way that always works, and it's not necessarily the shortest. We could try to work out a multiplication table. So we have the identity r squared, and r cubed. And those are the four rotations by pi over 2, pi, 3 pi over 2, and 0 radians. And we also have J, Rj, r squared j, and r cubed j. Now, these are just rotations. So r power of I times the power of I, just by the rule of exponents, is r to the sum of the powers. You can calculate all of these, and you'll see that everything you can get by multiply something here by something here is something else in this group. So this set is closed under multiplication. And you can also write down an inverse, because the inverse of j is j, and the inverse of r is r cubed. But there's an alternative way to show we have a group, and that's to show that these rotations and reflections all correspond to symmetries of the square. So here we have a square, 1, 2, 3, 4. And what are the symmetries of the square? Well, they're all the rotations around the center by pi over 2. So if you rotate this by pi over 2, you get 1, 2, 3, 4. Call this r. You rotate it twice, that's r squared. 1 goes to 1 goes to 1. You have 1, 2, 3, 4. You rotate it again, that's r cubed. 1, 2, 3, 4. Rotate it a fourth time, you get the identity. But we also have reflections. For example, let's say J is this vertical reflection. So when you rotate this vertically, 1, 4 ends up here, and 2, 3 ends up here. If you rotate the square horizontally, 1, 2 on the bottom is on top, 4, 3 on the top is on the bottom. You can also fix the lower left and upper right corners and rotate through the diagonal. 1, 3, but then 2 and 4 are interchanged. You have 2 and 4. And finally, you could rotate through the anti-diagonal or the opposite diagonal. So we're fixing 2 and 4, and 1 goes to the top and 3 goes to the bottom. So these are the 8 symmetries of the square. And one can establish a one-to-one correspondence between these symmetries of the square and those matrices that were constructed a moment ago. So, well, there's still a lot more work to do just to check everything here. And maybe I will stop at this point and continue with this in the next talk.